Alrighty, gang. Good morning and welcome back to MAC2312, section 004. That is Calc 2. Sorry, I just keep getting phone calls. It's just one of these days. I will be right there. Let me get rid of those folks. All right, we're back. So apologize if my voice sounds a little bit weak today. I am definitely sick. I think whatever it is my son has been passed to both my wife and myself. And let me tell you, it is some miserable shit. But we got him and the wife COVID tested, so I'm pretty sure it's not COVID. That's nice. Just normal sore throat bullshit. Is I may just be speaking a little more softly today than usual, which I don't imagine will cause anybody any distress. Last time we talked about finding volumes using the disk washer method. Today we will talk about finding volumes using the cylindrical shells method. I'll do my best to contrast the two methods for you and help you remember how they work, and I'll show you some kind of visualization tools to help you see how those methods are really calculating the volumes that we want them to be calculating. Let me get the doc cam flowing and we can do the thing. Timestamps, help us keep track of that shit. Zoom in a little bit. We're on the move. So this is MAC2312. Section number 004, which is a Calc 2 class, and the date today is the 12th of January, 2022. Today, I'll be talking about volumes. Cylindrical shells. That is blurry as all hell. Okay, come here. Come on. There you go. Okay. And this is section 6.3. So I actually want to start with a specific problem from section 6.2, which is a disk washer problem. It's about as challenging as any problem that could, for example, show up on a test. And it is also a nice problem to contrast the two methods on. So I'm going to take a particular problem, solve it with the disk washer method that we learned last time, and then solve that same problem again using the cylindrical shells method to try and show you why in certain instances it is superior to use the one method over the other. Of course, between those two events, I'm going to have to tell you what the cylindrical shells method is and where it comes from in order to employ it on that problem. So first, let me grab your textbook. Pull up the problem, which if I remember right is number 19 in 6.2. which one was it? 16, this is the one. Okay, so we're going to solve this problem as kind of a warm-up, reminding us how to do 6.2 stuff, and then I will show you why it is so much better to do this problem the other way. So what we're going to do is we're going to find the volume of the solid obtained by rotating the region bounded by the curve x times y equals 1, y equals 0, x equals 1, and x equals 2, about the axis of rotation, x equals -1. Of course, it's important you know what all of these look like. The first one here especially might be a little tricky. So let me just get this written down and we can get to it. So first we're going to do this disk washer problem. Like I said, I'm not going to write all the words. Find the volume, blah, blah, blah. The curves are x times y equals 1, y equals 0, x equals 1, x equals 2, and we're going about the axis x equals -1. Remember, I'll deal with this in a minute. Y equals a constant. That's always a horizontal line. So this y equals 0, that's actually the x-axis. X equals a constant, like x equals 1 and x equals 2. Those are vertical lines. Before I do that, if you divide both sides by x here, you see that this is the same as y equals 1 over x, which is a curve you should know. This is one of your parent functions from the review material module. So let's get in here and draw our picture. Here's what y equals 1 over x looks like in the first quadrant. It does have a piece over here as well. All right, so this is the curve x times y equals 1, or y equals 1 over x. If I mark this as 1 and this as 2, and here's the vertical line, x equals 1. And here's the vertical line, x equals 2. This is x equals 1, this is x equals 2, and this is x times y equals 1. I'll write it as they have done. The line y equals 0 is the x-axis. So if you look at these three curves, or four curves, I suppose, there's only one region, right? There's many regions here. But there's only one that is enclosed by those three curves. And hopefully you can see that. It is this one. So this is the region they're asking us to rotate. Remembering the steps that I outlined for you before, your first steps are to draw the curves and identify the region. So that's what we've done here. Your next step is to draw in the axis of rotation, which in this case is the line, the vertical line, x equals -1. So this right here is my axis of rotation. All right, and this is where you should begin. Got a nice picture. Are there any questions about where this picture comes from? Okay. We want to solve this using the dishwasher method. And remember, the big deal about the dishwasher method is that you come in here and you draw your strip perpendicular to the axis of rotation. So that's what we're going to do. I'm going to come in here to my region and draw a little differential thickness strip perpendicular to the axis of rotation. That is this strip. And hopefully you can see that if I rotate this strip about this axis, I will get a washer shape. So I'll do my best down here to sketch for you this washer shape. My art is bad and I feel bad. Something like this, right? It doesn't have to be perfect. Just good enough so we can tell what's going on. There we go. Is everybody with me so far? Yeah, I see some stuff in the chat. Right, so here's the y-axis, here's the x-axis. The curve y equals 1 over x, which is the same as x times y equals 1, is this curve. This is one of your parent functions. You need to know this. And then the line x equals 1 and x equals 2 are vertical lines going to the point 1, 0 and 2, 0 respectively. Finally, the line y equals 0 is the x-axis. It's a horizontal line. I draw in my strip perpendicular to the axis of rotation. That's the whole thing with the dishwasher method, is that your strip is drawn in perpendicular to the axis of rotation. And then I imagine rotating just this strip around this dotted axis of rotation here, which is the line x equals -1. So it told me that's my axis of rotation. The thickness of this strip, the little thickness here, is a vertical thickness, which means this is dy, right? The thickness of my washer. And then this washer has two radii, right? An inner radius and an outer radius. You can think of this axis of rotation as looking through here like this. So the inner radius is this, and the outer radius is this. And in order to find little r and big R, which we need to come back to our picture here and label them as distances. So first, just graph everything they give you, graph all this shit. Then identify your region, shade your region. Then draw in your axis of rotation. Then for the disk washer method, you will draw your little strip perpendicular to the axis of rotation. Imagine rotating just that strip, you get this washer shape. It has an inner radius and an outer radius, which we now need to find. Once we have those inner radius and outer radius, the volume of this little washer, the thing we call dV, is pi times the outer radius squared minus the inner radius squared times the thickness, which here is dy. Since this thickness is a dy thickness, I know that I need both big R and little r as functions of y. Right, my integral is going to be a dy integral, which means I cannot have any x's in there. It has to all be y stuff. The inner radius is easy to imagine. The inner radius is easy to find, I should say. It is this distance. And remember, we're thinking of this as a function of y. We need to know what is this radius everywhere through here. So if the strip was up here, what is the inner radius? If the strip was down here, what is that inner radius? Can anybody help me with little r? What is the distance from the near end of the strip to the axis of rotation? Very good. So I got three different answers there. Two of them are correct. One of them is correct for the outer radius, but not the inner radius. So we're looking for the inner radius right now. That is this distance. And what you notice is that no matter where the strip is, if the strip was down here, if the strip is where I've drawn it here, or if the strip is at the very top of this region, that inner radius, this distance, is always just the distance from the axis of rotation, x equals -1, to this leftmost boundary, which is x equals +1. This distance is 2, right? You take the x value here, which is 1, and subtract the x value here, which is -1. So the inner radius is 1 minus -1. And on a good day, that's 2. The outer radius, which King answered correctly in a sense, is more complicated. So what I'm going to do, I'm going to zoom in a little bit here. And I'm going to label this point right here, because this point, it turns out, is very important for this problem. This is the point on the curve y equals 1 over x, where x is equal to 2. So the x coordinate there is 2, and the y coordinate is 1 over x, which is 1/2. If the strip is above this point, then capital R, which the outer radius is this distance, right? Then capital R comes from this point on the curve where the strip hits this curve. But if the strip is below this point, like down here, then capital R is constant. So in other words, capital R here is a piecewise function of y. Capital R is somewhat complicated. I'll say that again because I want you to get it. if the strip is above this point, remember we have to think of the strip as moving through this region. If the strip is above this intersection point, then capital R is the distance from horizontal distance from this curve to the axis of rotation here. If the strip is below this intersection point down here, then capital R would be the distance from this vertical line to this vertical line, which is constant. So capital R actually depends on whether you're above this point, like in this part of the region, or below this point in this part of the region. So I'm going to split this into two cases. If y is less than 1/2, that's below this point, or if y is greater than or equal to 1/2, that's at this point or above. If the strip is below this point, if y is less than 1/2, then capital R is just the distance from here to here, which is the distance from 2 to -1, which is 3. However, if the strip is above that intersection point, we need to play this game where we characterize that point on the curve, and we need to do it in terms of the variable y. So if I solve x times y equals 1 for y, I get y equals 1 over x, which is what I use to graph this curve, because I know what that curve looks like when I write it that way. I could also solve this for x by dividing both sides by y, and I would get x is equal to 1 over y. So this point on the curve, I can think of as 1 over y, that's the x value there, comma y. That's this point where the strip touches that curve. In particular, what I'm saying is that if y is bigger than 1/2, then the outer radius, the distance from the far end of the strip to the axis of rotation, is the x value here, which is 1 over y, minus the x value here, which is -1. That's 1 over y minus -1, or 1 over y plus 1. So this is a challenging problem to set up using the disk washer method, because capital R is a piecewise function, right? You have to split it up. You have to take care of this part separately from this part. For this part, capital R is constant, it's just 3. But for this part, capital R is 1 over y plus 1. And what this means is that you're going to have to split up the integral. Now, overall, let's talk about this integral. I would integrate dv from the smallest y value in my region to the largest y value in my region. This point right here is 1, 1, where 1 over x hits the line x equals 1. So my integral for the volume is the integral of the little volumes taken from y equals 0 all the way up to y equals 1. And the issue is that dv, which is pi times big R squared minus little r squared dy, is different if y is smaller than 1/2 or if y is bigger than 1/2. So we will need to split this integral up as the integral from 0 to 1/2 of dv plus the integral from 1/2 to 1 of dv. Because dv is different when y is bigger than 1/2 compared to when y is smaller than 1/2. dv is always pi times big R squared minus little r squared dy, but big R changes when y is smaller than 1/2. So from 0 to 1/2, dv is pi times big R squared, and big R is 3 if y is smaller than 1/2, so it's 3 squared, minus little r squared, that's 2 squared, times dy. This is this first integral, plus integral 1/2 to 1. Now y is going from 1/2 to 1. This means y is bigger than 1/2. So big R is 1 over y plus 1. So dv is pi times 1 over y plus 1 squared minus little r squared, which is still 2 squared dy. And let me back up a little bit here and you can kind of see it all together. This is the hard part for this problem for sure. This is the hard part for all of these problems, setting them up. I'm going to give you a minute just to get things written down. Make your first priority getting this shit nice, neat, clear, correct into your notes so that you can look it over later. Once you have that, ask questions. So take a second, make sure you have on your paper everything I have here. Make sure it's correct. All right, in a second, we will solve both of these integrals. Okay. I'm trusting now that most of us have gotten down to here with everything correct in their notes. I want to take a second to answer questions on this. We understand what's going on with capital R here. Any questions about why capital R is piecewise or where these pieces come from? How did I get 3? So if my strip is down here, right? See this little highlighted spot? If my strip is down here, then capital R is the x value here minus the x value here. The x value here is 2. The x value here is -1. I can do this off to the side. So if the strip is below the point 2, 1/2, then capital R is the x value here minus the x value here, which is 2 minus -1, which is 3. And if the strip is above that point, then capital R is the x value here minus the x value here. The x value here is 1 over y. The x value here is -1. So this is 1 over y minus -1, or 1 over y plus 1. So these two observations is where this comes from. Yeah, that's the idea. That's the idea. Basically, this region, you guys remember some of those areas between curves problems, you had to split up. You couldn't do them all as one integral because the boundary curves in part of the region were different than the boundary curves in the other part of the region. Well, here it's the same sort of thing. In this region, above this intersection point, the boundary curves are the 1 over x curve and x equals 1, x equals 2. Below that intersection point, the 1 over x curve doesn't matter. The boundary curves are just x equals 1 and x equals 2. So the boundaries are different up here than they are down here. And that's what gives us the different values of capital R, depending on whether the strip is above or below that intersection point. So this is the tricky part, getting this realizing that means you need to split up the integral, and then getting these by plugging into our formula for dv. Careful, Sean, it's not a -2 all squared. Remember, capital R squared minus little r squared. So capital R is 3 in this first piece, and little r is always 2. So I'm subtracting, here's big R minus little r, right? And the r's are squared, so big R squared minus little r squared. And then here is big R squared minus little r squared. So only the 2 is being squared. The negative is not being squared in either of those expressions. But yeah, that's what's going on. Okay, these are good questions. Keep them coming. Any other hesitation getting to this point, right? I could put this problem on the exam. If I put this problem on the exam, you're gonna be like, shit, I wish I asked. Any other questions about how we get here? Okay, then let's go ahead and solve these integrals. We'll see what we get. Then I'll introduce you to the other method, which I claim is the superior method for this problem. And you'll see if we can get this much better. 3 squared is 9, 2 squared is 4, so this is 9 minus 4 is 5. So that first integral is the integral from 0 to 1/2 of pi times 5, which is 5 pi dy, plus integral from 1/2 to 1 of pi times. If I FOIL this out, this is 1 over y squared, which is 1 over y times 1 over y, or 1 over y squared like that, plus 1 times 1 over y, plus 1 over y times 1, that's plus 2 times 1 over y, plus 1 squared is 1, minus 2 squared is minus 4 dy. So all I did going from here to here is clean up these constants. This is 9 minus 4 is 5. Pi times 5 is 5 pi. And then here I FOILed out 1 over y plus 1 all squared. I can be more explicit about this if you want. This is 1 over y plus 1 times 1 over y plus 1, which is 1 over y squared plus 1 over y plus 1 over y plus 1. Gives me these 3 terms here. The integral of 5 pi dy is 5 pi and then y, right? The integral of dy is just y, evaluated from 0 to 1/2. Plus, I can pop the pi out of the second integral. Integral 1/2 to 1 of, I'll rewrite this in a form that makes it easier to see the antiderivative. 1 over y squared is y to the -2. I'll leave the 2 times 1 over y alone. Plus 1 minus 4 is minus 3 dy. All right, in this next step, I'm going to leave the first chunk alone. 5 pi times y, evaluated from 0 to 1/2. And now I'll cook up my antiderivative for the second piece. If you apply the power rule to y to the -2, you add 1 to that power, that gives you y to the -1, and then you divide by that new power. So it's y to the -1 divided by -1, which is -1 over y. This is the antiderivative for this. Plus 2 times 1 over y. Antiderivative for 1 over y is the natural log of the absolute value of y. So this is 2 ln absolute value y. And then minus 3, antiderivative for that dy is just minus 3y. And we're evaluating from 1/2 up to 1. Any questions on the antiderivative step here? Okay, we're going to continue from here. I evaluate each of these pieces between their bounds. 5 pi. When you plug in 1/2 here, you get 1/2, and you plug in 0 here, you get 0. So this is 1/2 minus 0, which is just 1/2. So that's going to be 5 pi over 2 plus pi times open big bracket. I'm going to plug in 1 here to everything, and then I'm going to plug in 1/2 here to everything and subtract the second from the first. So when I plug in 1, I get negative 1 over 1, which is negative 1, plus 2 times the natural log of absolute value of 1 is just 1, minus 3 times 1 is minus 3. So that's what I get when I plug in the upper bound to the second bracket. And now I need to subtract off what I get when I plug in the lower bound. Negative 1 divided by 1/2, that's negative 2. Two times the natural log of the absolute value of 1/2 is just 2 times the ln of 1/2. Minus 3 times 1/2 is minus 3/2. All right, so technically this is the answer, but it is not in a nice form. And at this stage, I could not yet give you full credit for the problem if you gave me this. There's one thing that I would require you to do, several things I would like you to do. The one thing I would require you to do to get full credit is to tell me this number. This is a number you should know. What is the natural log of 1? Thank you, Matthew. Yeah, the natural log of 1 is 0, right? Because e to the 0 is 1. The other thing that you really should do is combine any obvious like terms. Like I've got a bunch of integers here, I've got a rational number here. And the last thing, you can clean this up quite a bit as well. So let's do all the good stuff here. Let's get this in really nice form. I have the 5 pi over 2 from the first integral chilling, plus pi times. Now I'm going to distribute all the negatives and combine all the like terms. I have negative 1 minus 3 is negative 4. Minus negative 2 is plus 2. Minus 2 ln 1/2. And then minus negative 3/2 is plus 3/2. Negative 4 plus 2 is negative 2. So these two make negative 2. And now I want to add negative 2 to positive 3/2. Well, negative 2 is negative 4 over 2. -4/2 plus 3/2 is -1/2. It's -1/2. And then I've got -2 natural log of 1/2. There's one other thing I would like to do. There's this rule for the logarithm. If you have a constant out front multiplying a logarithm, that constant can come in as a power. What I want to do is bring the negative in. I don't mind the 2 here, but I really don't like the negative. I don't know what the natural log of 1/2 is, but I do know what the natural log of 2 is. You want a fun trick to remember the natural log of 2? It's an important constant. It shows up a lot. Natural log of 2 is about 0.69. Everybody's going to remember that, right? We love those 2 digits next to each other. Very nice. Natural log of 2 is a nice number. So let me let me pull this negative inside the natural log using this rule and distribute the pi. I get 5 pi over 2. Distributing the pi here, this becomes minus pi over 2. Distributing the pi here and bringing the negative inside, I get plus 2 pi times the natural log of 1/2 to the -1 is 2. And then 5 pi over 2 minus 1 pi over 2 is 4 pi over 2. That's 2 pi. So this is 2 pi plus 2 pi times the natural log of 2. Everything from here down is optional. All right, you get me to here, I'm happy. Full credit, 10 out of 10. I like this form much more than this form, because from here, it's not even clear that this is a positive number. And when I'm calculating a volume, I really want to know that I get a positive number. There's no such thing as a negative volume. From this line, it is quite clear this is a positive number. 2 pi is about 6. Natural log of 2 is about 0.69. So these are all positive. Okay. So the volume of the solid we get here is 2 pi plus 2 pi times the natural log of 2. Good show. But I think you'll agree that altogether, this is not a pleasant problem, right? Like there's an awful lot of shit going on here. We had to do 2 separate integrals. We had to split up the integral because capital R has different rules depending on whether my strip is above or below that intersection point. And then all this calculation work is quite a lot. I would like to not do that much work. Mathematicians are profoundly lazy people. I'll be the first to admit it. The way to spare yourself all this work is, rather than drawing the strip perpendicular to the axis of rotation, as we have done here, following the methods of 6.2, which is what this problem intends, it's a 6.2 problem, draw the strip parallel to the axis of rotation. Now that will give you a very different shaped little solid here. So this formula will no longer work. Before we come back and attack this problem anew, drawing the strip parallel to the axis of rotation, I want to play around a little bit with the difference in the shapes you get from a strip parallel to the axis of rotation compared to a strip perpendicular to the axis of rotation. And this is really the introduction to section 6.3. Okay, so if you draw the strip perpendicular to the axis of rotation, then you get the situation with which we are familiar, right? I'm just going to draw in here an axis of rotation and a strip, nothing else. You should put this all in your notes as well. This is where you will contrast the two methods. So if the strip is perpendicular to the axis of rotation, then the solid which is generated when you rotate just that strip will be a little washer. And this is what we've been seeing so far, because so far we've used just the disk washer method. You always draw your strip perpendicular to the axis of rotation. This thickness here, I'll just call dt, because it could be dx or dy, depending on the problem. This little distance in here is your inner radius, and this larger distance out here is your outer radius. And this is the disk washer method. Where dV is pi times your big radius or outer radius squared minus your little radius or inner radius squared times dt. And big R and little r are what we said they are in the previous exam, in the previous lecture. Big R is the distance from the far end of the strip to the axis of rotation. And little r is the distance from the near end of the strip to the axis of rotation. Okay. So that's your disk washer method, the method we've been using. If, on the other hand, you come in here and you draw your strip parallel to the axis of rotation, so I'm going to place my strip like this. Again, I'll just call the thickness of the strip dt, because it could be dy or dx, depending on the problem. When you rotate just this strip, what you will get is a slightly different shape. My picture is pretty trash, but remember, these strips, we should think of them as being really infinitely narrow, very, very, very narrow. So what you get here is what we call a cylindrical shell. Think of this as like a soup can with the top and the bottom removed. It has a very, very, very narrow wall, right? The thickness of this wall is the thickness of this strip. And what I need to do is find the volume of this little cylindrical shell. And the trick to that is to observe that this has a height and it has a radius. The radius is this distance and the height is this distance. Right, that yields this height, right, and a little cylindrical shell with radius like this. So this yields, drawing the strip parallel, yields a cylindrical shell. What those words mean, it's a shell of a cylinder, right? If you took a cylinder, but then punched out like all the middle, so you just had a very, very thin shell shaped like a cylinder, that's the shape we're talking about here. The key to finding the volume of this object is to imagine you have some very, very sharp scissors, some very, very sharp scissors, and you come in here and you cut this bitch up, and then you unroll it. Right, again, imagine that you have a soup can, right? A soup can with the tops and bottom removed. Then you cut along one of the sides and unroll it. So if you cut and unroll, instead of a cylindrical shell, you'll just have a little rectangular prism. It's very thin. That looks like this. The height is still the height. And this dimension here is still the little differential thickness of the strip. The question is, what is this dimension? So if I were to cut and unroll this shell into a long rectangular prism, what dimension of this object here is the length of this object here? Anybody help me with that? Yeah, very good. 2 pi times the radius. I'm using a lowercase r here, but it's the circumference. So what that means is that dV, the volume of this cylindrical shell, the thing that we would need to integrate to get the volume of our solid, is the length times the width times the height, which is 2 pi r times the height times that thickness, which is dt, either dx or dy, depending on the problem. And here, r is the distance from the strip. And there is no near end or far end, right? This strip is thought of as being infinitely narrow. So it's just the distance from the strip. The top is the same distance from the axis of rotation as the bottom. Distance from the strip to the axis of rotation. And h, the height, is literally just the height of the strip. If the strip is oriented sideways, you may end up calling it a length, but I'll always call it just the height of the strip. Okay, so these are the two methods, guys. 6.2, 6.3. Disc washer, cylindrical shells. You might ask, this is a washer, not a disc, right? What happened to the disc? Well, if little r is 0, then this is a disc, right? If there is no gap between the strip and the axis of rotation, then there is no like gap in here, and you just have a disc instead of a washer. So really, this is everything. Everything we've talked about for volumes is encapsulated on this page. This is everything you need to remember in order to solve any of the problems from section 6.2 and 6.3. And you do need to remember this stuff. When people ask me for formulas, is there a formula I can memorize? Here it is. Here's the formula for the cylindrical shell stuff. Here's the formula for the disc washer stuff. All right, specifically this and this, this and this. If you remember that, you're good to go. Comments, questions? Okay, as I promised, I'm going to go back and solve that previous problem using the cylindrical shells method, and you'll see that it goes much, much, much nicer. Before I do that, I want to help you visualize the solids, the total solids, as a combination of these things. There's a tool I've posted for you in the modules. And I want you to check these out. Remember, every section that we cover in this textbook, I have lots of shit for you in here to look at, lots of videos of people solving more example problems. Lots of things that will help you visualize what's going on, right? We've got like 3 cylindrical shells examples you can watch here, 3 disc washer examples, 4 disc washer examples you can watch here. And then we've got the Paul's online notes where he talks about the 2. The things I want to show you right now is how you can think of these big solids as being a bunch of these little objects stacked up. So here's an example for the disc washer method. I'm just going to show you a few seconds of this.
Okay, we want to find the volume of the solid formed by rotating around the x-axis, the region formed by
x equals 1. So we're talking about this tiny little region here. We're going to rotate it around the x-axis. To get a better idea of what's going on here, let's take another look at this. So here's my y equals x squared and my y equals square root of x region. There is a representative little slice, and what we're doing is we're rotating that piece around the x-axis, and you notice that that's going to give us this donut shape, well, washer.
All right, so you see he's got his region here, his little strip that's drawn in perpendicular to the axis of rotation. He's rotating about this x-axis. And when he does that rotation, when he rotates just that strip, he's getting a washer shape.
Shape is what we call it. It's a large circle with a hole in the middle, right? And for each slice of this curve, we will get a rotated washer.
Region as having a strip moving
if we
through
get
it.
a whole bunch of those,
one of those strips generates a different washer.
We get a whole bunch of those little slices,
and
we rotate them all,
we're going to get the whole
then
shape,
we're going
or
to
at least
get
something very close
our
to the
actual
solid.
shape,
There
or
it
at
is.
least
Boom.
a good approximation of it. In the long run, we're going to get the actual shape, which we see there. So let's see what's going on here. So going back, you'll notice we rotate those.
One strip, one washer.
We get a whole bunch of those little slices, or at least a good approximation of it. In the long run, we're going to get
the. Of course, you need infinitely many strips to get the exact volume, but that's what the integral does. Here's the same thing, but for cylindrical shells.
Okay, we want to around the here, even though we
could,
if we really wanted to, we could change the problem to be a horizontal slice and use pins here. So we get a different shape curves. There's our slice, and if we start revolving it, notice we get a different shape than we did before. Before we got a flat washer, here we're getting sort of a thin shell. And so this is called shells or cylindrical shell method. If we take a whole bunch of these shells now,
you use a shitload of these all at once instead of just one,
a whole bunch of slices, and revolve them all, you'll see how those little cylindrical shells sort of stack up,
and those stack up or nest inside one another to give you the whole solid.
And then in the limit, it would give the actual
and then
volume.
In the limit, the integral will give you
solid.
The whole volume.
Okay, so let's see. We know
that's the game. All right, and if you want to watch those in your own time, you can watch the whole thing. So I just wanted to show you how you can think of all of your solids as either being a bunch of these things stacked up or a bunch of these things stacked up. All right, but again, this is what you need to remember for the disc washer method. This is what you need to remember for the cylindrical shells method. And those links are in the modules. There's a good question from Quinn in the chat. Do we need to worry about our region crossing over the axis of rotation? Theoretically, certainly there could be problems like that, but you will not see any in this course because they complicate things quite a bit. So no, you will not need to worry about your strip or your region crossing through the axis of rotation. At the worst, the closest you'll get to that is your axis of rotation touching up against that region at one of the endpoints, but you'll never have the axis of rotation inside the region. Okay, so let's return to this problem now. But instead of solving it with the disk washer method, which we've seen is quite complicated, right? Lots of integrals, big messy shit. Let's attack it using the shells method. Again, I'm gonna draw my curves and my region. That's always what we need to do. Draw on my axis of rotation. Here's my y-axis. Here's my x-axis. The curve x times y equals 1 or y equals 1 over x still looks like this. I'm not going to bother drawing the part down here because I know it's not relevant to the problem. I'll say this is x equals 1. I'll say this is x equals 2. So here are those two other boundary curves. X equals 1. X equals 2. There are vertical lines. X equals a constant on this vertical line. This is the curve y equals 1 over x. This is the line x equals 1. This is the line x equals 2, which means my region. Still this region. And then my axis of rotation is the line x equals -1. I'll draw it in dotted. This is what we're revolving around. The big difference is that now I draw my strip parallel to the axis of rotation. So I come in here and at an arbitrary location within my region, I draw a little differential thickness strip, this time parallel to the axis of rotation. Like so. The thickness of that strip is a dx thickness, right? Because it's a vertical strip, so that little thickness is a little change in x. If I were to revolve just that strip, I'm not going to draw it full size here, but if I were to revolve just that little strip, of course, I would get a little cylindrical shell. Looking something like this. It has a height. It has a radius. And it has a wall thickness, which in this case is dx. The height of that shell is the height of this strip. And the radius of that shell is the distance from that strip to the axis of rotation. The point where this strip touches this boundary curve since I'm doing everything dx this time, I don't need to like solve this for x and write it in terms of y. I just think of the point on this curve as x comma 1 over x, right? X comma f of x. So that height is the y value here minus the y value here. The y value here is 1 over x. The y value here is 0. So my height is 1 over x. The radius is the x value here minus the x value here is the horizontal distance from my strip to the axis of rotation. Well, the x value here is x, and the x value here is -1. So the radius is x minus -1, or just x plus 1. And then following the work we just did, the volume of that shell is 2 pi times the radius times the height times the differential thickness, 2 pi RH dx, which is 2 pi times r is x plus 1, h is 1 over x, dx is dx. And then I'll need to, in order to get my total volume, I'll need to integrate that from the smallest x value in my region, leftmost position of that strip, which is 1, to the largest x value in my region, the rightmost position of that strip, which is 2. So my total volume is the integral from x equals 1 up to x equals 2 of my little volumes, which is the integral from 1 to 2 of 2 pi times x plus 1 times 1 over x dx. Can anybody help me with this integral? How do I do this integral? This is nowhere near as bad as the last one. Anybody want to give me just one step? What's the first thing we would do with this integral? Good. Sean suggests we pop out the constant, which is 2 pi. Let's do that. It's a great idea. 2 pi comes out. 2 pi integral 1 to 2. And then what's left is x plus 1 times 1 over x times dx. Okay, how do I do that? What is my next step? Good, we distribute the 1 over x over the x plus 1. All right, I need to do out this multiplication. I cannot integrate these separately. They're multiplying, right? Just like if you're going to differentiate a product of two things, you need a product rule. We don't have a product rule for integrals yet. So the only way we could hope to anti-differentiate this is to distribute and clean it up. So I'll get 2 pi integral 1 to 2. 1 over x times x is 1, plus 1 over x times 1 is 1 over x dx. Now this, I do need to know how to find an antiderivative for. Antiderivative of 1 dx is just x, plus antiderivative 1 over x dx is the natural log of the absolute value of x. And we evaluate from 1 to 2. Plugging in 1, I get 1 plus the natural log of 1. And then, oh, sorry, I should plug in 2 first, right? 2 is the upper bound, I'm so sorry. So that's 2 plus the natural log of 2, my upper bound. And then I subtract off what I get when I plug in 1, which is 1 plus the natural log of 1. Again, the natural log of 1 is 0. This guy goes away. So I get 2 pi bracket 2 plus ln2 and then minus 1, or 2 pi times 1 plus ln2. And then distributing the 2 pi, that's 2 pi plus 2 pi times the natural log of 2. See how much nicer this is? All right, I get straight to this beautiful form of the answer. Very little work. This integral is much, much easier than the integral we did the other way. Also, this setup is much, much simpler, right? There is no recharacterizing this point in terms of y. There is no splitting the integral up based on whether you're above this point or below this point. In fact, I never even needed to find the coordinates of this point. None of that mattered. So the Shells method is certainly the better method for solving this problem. If you want a screen cap, yeah, everything. All right, so here's the first part. All right, everything up to the setup of and simplification of the integral. And then here's the solving and evaluating of the integral. Pay attention to the notation, and please try to use good notation in your own work. And it is very important that your notation is understandable. We don't want a bunch of shit scribbled all over the page. We want a good, clean workflow where I can go, okay, you did this, 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 like one thing after the other. To complete a long journey, you don't need to be able to do the whole thing at once, right? To climb Everest, you don't climb Everest at once. You just take the next step, and then the next step, and then the next step. You don't need to know that the answer is 2 pi plus 2 pi natural log of 2. You just need to know that to go forward from here, you distribute the 1 over x. And to go forward from here, you find an antiderivative, and so on. Okay. So for some problems, like this one, the Shells method is the better method. The Shells method comes from drawing your strip parallel to the axis of rotation instead of drawing your strip perpendicular to the axis of rotation. And again, here is everything you need for the two methods. I'd like to solve at least one more problem using the Shells method here. This last problem we looked at was unpleasant if you set it up with the disk washer method. It was bad set up by the disk washer method, and it was nice set up by the cylindrical shells method. The next problem I'm going to show you is impossible using the disk washer method, and very nice with the shells method. A neat function here. So again, find the volume. Blah, blah, blah. Boundary curves are y equals the sine of x squared. Weird function, probably not a function you're super familiar with. Focus. From x equals 0 to x equals the square root of pi, rotated about the y-axis. Sine of x squared, understandable if you're not familiar with it. Let me show you in Desmos really quickly. Before I do that, qualitatively, you know, sine, this is going to give you a wave, right? It's going to have a min of -1 and a max of +1. It's some sort of wave. But with x squared inside, instead of just x, with x inside, it's like a steady wave, right? We call them sinusoids, just a nice steady wave with a constant frequency. X squared grows faster than x, right? When x is close to 0, x squared grows pretty slowly. When x is big, x squared grows pretty quickly. So what that means is that the frequency of this sine wave is going to be very low at first and very high later on. I'll show you in Desmos. So I'm expecting a sine wave. Near x equals 0, the frequency should be quite low, meaning waves are far apart. And far away from 0, the frequency should be quite high, meaning waves close together. Here's sine x. Here's sine x squared. Frequency starts out quite low. And then as you move further and further to the right, the frequency increases. That's quite large. I'm only interested in what's going on from 0 to this point, which is the square root of pi. Right there. In other words, my region that's my region. Square root of pi is a really neat number, by the way. This is also the integral from negative infinity to infinity of e to the negative x squared. It's a very special number. If you're ever on PSN or any sort of gaming systems and you see a user square root pi, that's me. All right. So let's draw our region. Again, I'm only interested in what's going on from 0 to the square root of pi. I'll mark this as 1. So there's this curve from 0 to root pi. And it does continue, it does the same sort of thing over here. It's an even function. It goes down here. I don't care about any of that. Here's our region. There's my region. My axis of rotation is the y-axis. I'm rotating that region about this. You can kind of picture the sort of solid we're going to get from this. It's going to have like a concave bowl inside, and then it's like rimmed on the top, and then it's poofy on the outside. So it's kind of like if you had a donut where the donut hole in the middle is very, very small, and then you just sliced off the top. That's what the solid we're going to get looks like from this. But you don't need to be able to visualize the whole solid to calculate its volume. You just need to follow the rules. So you draw on a little strip parallel to the axis of rotation. I claim that this problem is impossible to set up using the disk washer method. I'd like you to think about why that is. If the strip was perpendicular to the axis of rotation going side to side, first off, you'd have to solve this for x in order to find the x values here and the x values here. That's a problem. Your very first step there would be to take the inverse sine of both sides. That comes with some domain restrictions, and we would be outside the allowable domain for that. Worse, this function is not one-to-one, right? This function is not one-to-one. So when you solve this for x, that solution would only work at best up to here, like from 0 to the square root of pi over 2. It would not be valid over here. So it really is impossible to set this up using the disk washer method, but you'll see that it's very, very easy to set up using the cylindrical shells method. If you rotate just that strip, you get a little cylindrical shell. All right, looking like this. The wall thickness here is the thickness of that strip, which is dx. The height here is the height of that strip, which we get by thinking about the point up here. And we're along the curve y equals sine of x squared. So this point is x comma sine of x squared. So that height is the y value here minus the y value here. That's the sine of x squared. The last thing we need is the radius, which is the distance from the strip to the axis of rotation, which is this. And that radius what is that radius? What is the distance from the strip to the axis of rotation here? What is this horizontal distance? This point is x comma sine of x squared. What is this horizontal distance? Yeah, very good. Just x, right? It's the x value here minus the x value here. The x value here is just x. The x value here on the y-axis is 0. Remember, the y-axis is the line x equals 0. So the radius is just x. This means that dv, the volume of this little cylindrical shell, is always 2 pi rh. In this case, the differential thickness is dx, which is 2 pi x times the sine of x squared dx. Which means that my total volume V, always the integral of dV. In this case, we're going from 0 up to the square root of pi, right? From the smallest x value in my region to the largest x value in my region. So it's from x equals 0 up to x equals the square root of pi, which is integral 0 to root pi 2 pi x sine of x squared dx. And now I ask again, how do we do this integral? It's not bad, but you may have to think about it for a minute. What is my first step? Remember, you can hold spacebar to talk. Feel free to shout out. I want a conversation here.
Pull out the constants.
Yeah, and I think that's what you're saying in chat, Fabrice, right? We can pull out the 2 pi. The 2 pi is a constant. And then I'm left with integral 0 to root pi of x sine of x squared dx. Now I'm left with this that I need to find an antiderivative for. And I want you to think about last week's lecture. How would you find an antiderivative for this? How would you integrate x times sine of x squared? Does anything jump out at you?
Something is better than nothing, but I'm just trying to look at the better before it's ready.
So there's a suggestion in chat to make a substitution. I'll say real quick, yeah, okay, good, better. So subbing z equals x or u equals x, that will never change anything, right? If you just make the substitution u equals x or z equals x, then everything stays the same. You're just relabeling the variables. But here, if we make the substitution, I'm going to use the letter z. Remember, we talked about y last week. Z equals x squared. Then dz is 2x dx. And I do have an x here that will cancel with that. The other thing we need to do is change our bounds. So my old lower bound is x equals 0. My old upper bound is x equals the square root of pi. I told you we're going to use substitution all semester long. That's 100% true. You need to get good with this stuff. When x is equal to 0, z is equal to 0 squared. And 0 squared is still 0. So my lower bound will stay 0. When x is equal to the square root of pi, z is equal to the square root of pi squared, which is just pi. So my old lower bound is my new lower bound. Those don't change. My old upper bound is root pi. My new upper bound is pi itself. The other thing here, I'm going to, before I implement this substitution, I'm going to rewrite it like this. I've got 2 pi integral 0 to the square root of pi sine of x squared times x dx. And I'm doing this to show you kind of the nice way to implement a substitution. If you take this dz equals 2x dx and write it as 1/2 dz equals x dx, you see right away that this piece, x dx on the far right, is 1/2 dz. So plugging in my substitution, I get 2 pi integral 0 to pi. Sine of x squared is the sine of z. And x dx is 1/2 dz. Now this 1/2 will pop out and cancel the 2 up front. So I have pi integral 0 to pi sine of z dz, and this you could do back in Calc 1. What is an antiderivative for the sine of z? Just underlining here. So if you take a screenshot and review this, you can see where everything comes from. What is the antiderivative we use for sine of z dz? Very good, negative cosine of z in the dm. Negative cos of z. And we have to evaluate this from 0 to pi. You do not plug back in x squared, right? You don't do that. You just evaluate this between the new bounds. That's why we changed the bounds. It's part of why we changed the bounds. We had a long discussion on why we do that last week. All right, now it's time to evaluate. I'm going to open up over here to give myself some more space. Pi. This is negative cos of pi minus negative cos of 0. Now we're going to see how well you guys remember your unit circle. What is the cosine of pi? Thank you, Sean. So the cosine of pi itself, that's -1. What is the cosine of 0? +1. Very good. So what I have here is -1, +1, minus -1. So this is pi times -1 is 1, minus -1 is +1. In other words, this is 2 pi. All right, that's it. So I'm going to back out here a little bit. If you want to take a screen cap so you can review this for your notes, here's the first part of the problem. Statement, sketch, integral setup. Take a screen cap if you want. In 5 seconds, I'm going to scroll down so you can cap the bottom half. And here's the lower half, just the integral. Okay, this is where we're going to end today's lecture. On Friday, we're going to talk about a concept from physics called work. Work is the amount of energy that's needed to like move an object or do some sort, I don't want to say the word work in the definition, but to accomplish some movement resisting some force, or perhaps working together with some force. So it's a physics thing, but it turns out that you calculate it by using an integral. So one of the kind of simpler and more tractable applications of integral calculus to physics is the calculation of this quantity called work. Next time, that's what we're going to do. So please, between now and Friday, I would like you to work some of the 6.3 problems in the homework, at least 2 or 3 of them. Make sure you have a feel. Of course, you should have worked several of the 6.2 problems by now. If you have not, please do those first. By the time you come to class on Friday, I want you to have worked at least 2 or 3 6.2 problems, at least 2 or 3 6.3 problems. And that way on Friday, you'll be in a good headspace to talk about this concept in 6.4 called work. That will be the end of our week. So today I do have an office hour from 1 to 2 p.m. You want to come chat with me, we can do it there, solve problems, talk about grades, whatever it is you want to do. Otherwise, I will see you guys on Friday at 11:10, and hopefully my voice will be a little better by then. That's it from me for today. Hope you guys have a lovely rest of your day. And again, if you need to see me, talk about anything, help with anything, office hours today, 1 to 2, tomorrow, 11 to 12. That is it. Take care.